Hey everyone, welcome back. So today we'll be talking about the EM, or the Expectation-Maximization Algorithm. Now I have an interesting relationship with this algorithm in that it was really hard for me to learn, and I think that is because of the way it's typically taught in the online resources I looked at least, or in the courses I had in grad school. And that is that they start from this very mathematical definition of the algorithm and maybe give you a proof of convergence and things like that, but nowhere along the way did that really make me understand the intuition or the idea, the cases in which I would want to use this. And so we're going to hopefully resolve those issues today by starting from the intuition, starting from what I think is a very simple use case. And then we'll move from there through into the math and all that. So we'll talk about the math. But the main thing I want you to get across in this video is mostly just in what sort of cases would I want to use this algorithm? And hopefully that'll be more clear in just a moment. So we'll actually start with a very basic question here, and then move our way through a series of more complicated questions, which will necessitate the need for this EM algorithm. So the first question is this. I tell you that there's 3 data points. So we have 1, 2, and we have a mystery data point x. So you just have 3 data points, and here they are. You know 2 of them, you don't know the final one. And I tell you that they are draws, they are independent draws from a normal distribution with mean and variance that are both 1. So normal 1, 1. Now based on all the information I just told you, what is your best guess for this missing data point x? So this can be seen as a kind of simple case of a missing data problem. When you have some data that is present and some data that's missing, and you assume that it follows some distribution here, what is your best guess? And this is not too tricky of a problem if you think about it for a couple minutes even, which is that, okay, each of these are independent draws, so I don't actually even need to consider the other 2 data points in this specific case. I can just say that x is a draw from a normal 1, 1. And what is the most likely value that is drawn from a normal distribution? Well, of course, it's the mean of that normal distribution. So if I had to give you just one prediction, one estimate for this missing value, I think the most sensible thing would be mu, which is equal to 1. Okay, so we have mu equals 1 here. Let's move on to a different problem, a different but related. This is kind of the opposite of this problem, which is that now I give you all the data. The data is all present. I tell you that you have data points 0, 1, and 2. No missing data here. Now the thing that's missing, now the thing that you don't know, is the actual mean of the normal distribution that generated this data. So I say that these are draws from a normal distribution with some unknown mean, mu, and again, variance 1. And the question now is kind of turned on its head. It's not what is the value of the missing data, it is what is the value of the parameter which generated all the data that's present. What is your best guess for mu? And again, this is not too tricky to think about. You can kind of stare at this for a second and say, if I just have 3 data points, and they're each independent draws from a normal distribution, my best guess for the parameter mu is going to be the average, the empirical average of these 3 data points. So if I take these 3 data points, add them together and divide by 3, I'm going to get 1. So my best guess for mu is going to be 1. All right, so these seem like kind of fun but silly questions, but they become very important when we look at this follow-up question, which doesn't seem too much more complicated on the surface, but then you really start thinking about it and it kind of seems like a chicken and egg problem. So let's just get into that. So the main intuition, the main problem that's going to form our intuition in this video is this one here, which is that now I'm doing both of these things at once. So in other words, I tell you that 1, 2, and x, again, x is unknown missing data, are draws from a normal distribution with some unknown mean mu and standard deviation variance 1. And now you see both of these things are missing at once. I don't know the average of the distribution that generated the data, and I also don't know one of the data points themselves. So it's strange because if you told me mu, we showed that I can give you a good estimate for the missing data. On the other hand, if you told me the missing data, I can give you a good estimate for mu, but how do I do both at the same time? It seems like a chicken and egg problem. I need one to get the other. How do I do both of these simultaneously? And now this brings up the spirit of the EM algorithm. So we're still not going to get into the math just yet. I'm going to do a simpler form of the EM algorithm with you all here. And just kind of doing it in a game-like fashion, which is that we'll go through the main high-level steps of what we'll eventually call the EM algorithm. But we're going to do it as kind of just us trying to guess our way through the dark with somewhat of a process, hoping that we converge to the right solution here. So let's start by just guessing some mu naught is equal to 0. So the subscript 0 is just saying that this is my initial guess for mu. I really don't know what it could be, but based on the data I have, maybe 0 is a good guess. I'm going to guess that mu is equal to 0. Now, if I assume that mu is equal to 0 for a moment, then I fall back into this case where I know mu. So in this case, I'm assuming it's 0. And so I can give you a good estimate for x, which is, again, exactly that mu, because we're assuming these are draws from that normal distribution. So then x naught, the naught, again, is because this is my initial estimate for x, the missing value, is also likely 0. But we don't stop here. Let's go ahead. Let's just kind of rinse and repeat here. Let's update our mu now. So now we're going to assume that x naught is equal to 0. What does that mean that my mu1, so my next guess for mu, what's a good guess there? Well, now we fall back into this bottom case here where I actually have all the data filled in because I've said that x naught is equal to 0. So my present data for now would be 1, 2, 0. And my best guess for mu would be 1, the empirical average of those 3 data points. And then we just repeat. Based on that, then my best guess for x is now equal to 1. Based on that, my best guess for mu is again the empirical average of the present data so far, which is 4/3. And we can just keep going on and on and on. And it feels like this would converge. I haven't given you any mathematical proof that it would converge, but indeed you can prove, and if you just do this long enough, you'll see that the convergence happens exactly when the mu that you're currently estimating is equal to the empirical average, which is also equal to the data point itself. That will be the convergence criteria. That's pretty easy to check. Seems pretty intuitive there. And if we solve this equation for x and solve this equation for mu, and we get to those converged values, we'll put stars on them to say that's the converged value. They're both equal to 1.5. Now let's just do a quick sanity check to make sure this makes sense. Pretend that I told you that the value of the missing data x was 1.5 and mu was also equal to 1.5. Is that information consistent with each other? Well, if x was equal to 1.5, then the empirical average of these 3 things is 1.5, which makes sense for then mu to be equal to 1.5. And if mu is equal to 1.5, then I could totally buy that the 3 data points that were generated were the mean itself, and then some value that was lower than the mean by a little bit, and some value that was higher than the mean by a little bit. So this information is totally consistent. Again, not a proof necessarily that it's the best possible setup for these 2 things, but at least we showed that this kind of simple back and forth guessing process is going to get us to a good place, at least in this situation. And let me pause there because I will finish this video by talking about the actual mathematics and the actual statement of the EM algorithm, but you basically know it now. If you understand, first of all, that we would apply such a method in cases where we don't know 2 pieces of information simultaneously, so we don't know some parameter of the process that generated our data, and we also don't know some of the data points themselves, we don't know both of these things simultaneously, then this method, which we'll eventually call the EM algorithm, is a very powerful, very simple technique for us to just kind of take little baby steps, updating one after another, after another, after another, until we reach convergence in both of these things so that they become kind of harmoniously coexisting as very sensible values for these parameters. And notice kind of crucially here that we didn't do any calculus here. When we think about maximizing or minimizing or optimizing things, we typically associate that with derivatives, needing to take some kind of derivative, set that equal to 0, solve some kind of equation there. We haven't done any of that. And that, as we'll mention at the end of the video, is one of the big pros of the EM algorithm versus some method like gradient descent or gradient ascent, which can also be used to solve similar types of problems, is that if taking a derivative is extremely complicated, I wouldn't say in this case, this is a kind of baby toy example, not too bad, but you can totally have pretty real problems where taking a derivative is very annoying and difficult, and then setting it equal to 0 and trying to solve that algebra can be pretty annoying too. The EM algorithm can be a maybe slower, but easier to understand, good bet, kind of interpretable way for you to get to the solution nonetheless. So now, without further ado, let's get into the math itself, now that we understand the intuition here. So to get into the math itself, we'll define a couple of extra quantities here, which will make our lives a little bit easier when we define the actual algorithm. The first one here is the probability of some given value of the missing data point x, given that we have some kind of estimate for the mu that generated the data in the first place. And that is going to be distributed normally with mean mu and standard deviation or variance 1. And so I haven't actually said anything new here. I've just put a formula to what I've said before. Remember, what I've been saying before is that each of these data points is an independent draw from the normal distribution that has mean mu. That's exactly what I'm saying here. Given that you know the mean mu, then the probability distribution of your data point x is going to be normally distributed with that mean mu and standard deviation or variance 1. So that's exactly what we've been saying in words before, just putting a mathematical equation to it. Now the other key quantity that we want to quantify is the likelihood function. You will be pretty familiar with the likelihood function if you've watched any of our past videos on maximum likelihood estimation or gradient descent, any of these things, or maybe you know it from some other space. But the likelihood function, basically its job is to say that given some value of your parameter mu, or in general, just if you're doing any kind of problem, given some value of your parameters in general, what is the likelihood, what is the probability of seeing the data that you actually observed in the real world? So in this case, we're saying that given that you have some value for mu, what's the probability of observing the data x, 1, 2? And since these are independent draws, we can basically just multiply this quantity we stated up here, this probability of data given mu, for each of these things. So one term for x, one term for the static value 1, and one term for the static value 2, each of them, of course, given that the current estimate is this mu. Now we can do the same thing we did in those previous videos, which is take the log here. It's just a little bit easier to work with sums than multiplying a bunch of very small probabilities that can lead to some computational annoyances. So we can do that here. We can just take the log of this, and that becomes the log likelihood function. Okay, so nothing's really changed here. Added an extra L up front, so now it means log likelihood function, log likelihood function. Each of these probabilities has a log on it, and the multiplications have become sums. But again, since log is monotonic, we know that maximizing or minimizing the likelihood is the same thing as doing that to the log of the likelihood. So this is more just a convenience step here. Now let's get into the actual EM algorithm itself. It just has 3 steps. The first one is just an initialization that happens once, and the other 2 are the E, the expectation step, and then the M, the maximization step. And you just cycle between them until convergence in the exact same intuition, in the exact same fashion that we cycled between these steps, updating our x and updating our mu, until we reach some kind of convergence criteria. So the very first step is the same first step we had out here, which is guess some sensible value of your parameter mu. So guess some mu naught. And there's no given way you should choose your guess. I mean, if I had to have a criteria for this problem, maybe I'll just take the average of all of the data points I do have. In this case, it was just 1 and 2, so my best guess for mu naught would actually be 1.5 in the first place, but it can be a little bit off from there, and this algorithm would still definitely work here. So take your best guess from mu naught, and now I want to spend some time talking about the E step, because this, not gonna lie, looks pretty complicated and confusing. But of course on this channel, whenever we see an equation, no matter how complicated or confusing it looks, it always is trying to tell us some kind of story. So let's just try to extract the story from here to make this beast look a little bit less scary. So this is called the expected likelihood, or in this case, expected log likelihood, same thing really, function. The first and main thing I want to make clear about this function is that it is a function of mu, which is going to be the next value. So your goal right now is to figure out if my current estimate for the parameter is mu naught, what's my best update for that parameter? What should be the next value of that parameter? And therefore, this function, this expected log likelihood, is a function of that proposed next mu. And now let's dive into the actual form. This is an integral. We don't see many of those on this channel. We haven't done a good integral in a while. This is an integral over all possible values of x. In other words, all possible values of this missing data point x. So it could be problem specific, exactly what values this can take, but in general you can just say this is from negative infinity to infinity. So what we're doing in this integral, and what we're doing in any integral really, is you're just scanning over some variables. So we're scanning over all possible values that x could take. And again, this is because we don't know what x is. That is part of the problem here, is that we're trying to simultaneously figure out mu and x. So I don't know what x is. So what I'll do is scan over every possible value of x. And now let's continue the story by looking inside the integral, what's happening for each value of x that we're checking. The first thing that's happening is that we compute the probability of the current mu that we are looking at, mu naught, generating that value of x. So we're saying that I'm going to pretend for a second here that my estimate for mu naught is correct, that the mu naught is indeed the mean of the normal distribution that generated all this data. If that's correct, then what is the probability density of this x that we're currently looking at inside the integral for every step of the integral? What is the probability of that x being generated? Now the key insight here is that for some x values, this is going to be a pretty large probability density function. It's going to be very probable. For other x values, probably very extreme positive or negative values, this is going to be extremely unlikely. Why is that important? Because this probability here acts as a weight on the term that comes after, and the term that comes afterward is the log likelihood of seeing this particular x and the rest of the static data, 1 and 2, the probability of seeing that collection of data given mu, where mu, again, is the proposed next mean after mu naught. Now let me make sure we understand this, because I still get tripped up by this sometimes because there's so many variables floating around here. There's a mu naught, there's an x, there's an integral. But let's go back to the first thing that I was saying before, which is that this whole thing, as many variables as you might see floating around, is only a function of one thing, which is your proposed next mu, so this mu here. And so the story this is trying to tell, this is basically a weighted sum. An integral is just a glorified sum. It's just an infinite sum, right? So this is just a weighted sum. And the weight is the probability that this particular value for the missing data point is correct. That's this probability we just talked about. And the value here, so again, this is an expected value, so it's a weighted sum. The value itself is the log likelihood of seeing all of that data, given that your actual mu for the normal distribution that generated the data is this mu here, which again, this entire thing is a function of. So to hopefully help understand this a little bit better, if you understand this already, you're good to go. If this is still a little bit unclear, maybe this will help, because this reasoning kind of helped me, which is that let's say there's a certain x for which this probability is extremely small, very, very, very small, then it doesn't really matter what value this likelihood function takes, because this weight is so small that it's not going to be a major factor in this function's value. Now conversely, assume that there is some x for which this probability or this weight is very large. Then that likelihood function, the value of that log likelihood function for that x, is going to play a much bigger part in the value of this function, this expected log likelihood given the mu. So in other words, what this thing is doing, what this weighted sum is doing, is putting a high emphasis on the log likelihood values for x values for these missing data points, which seem the most probable at this point, given our best estimate for mu. So the one weird thing for me was that why is there a mu not here, but there's a mu here? It seems kind of weird. But the story that I've kind of built up around that is that this first term is kind of just our best estimate for which missing values are the most likely, given our current information about the world. And the second term here is basically interacting with that by saying that I want to care about the proposed log likelihood, given some other mu that I'm about to suggest next, exactly for those missing data points whose probability seems high right now. And that is very much in the spirit of what we're doing with this more kind of verbal example up here, which is saying that for the x value that I currently think is a good idea, let's go figure out what mu value would be a good idea based on that. This is just doing it in a more probabilistic fashion. Okay, so I do encourage you to pause, kind of write this out for yourself, rewind if you need to, because if you understand this function, and you understand that it's a function of the next mu that we're going to propose, you pretty much understand the EM algorithm, because the next step, the M, the maximization step, is literally just saying, give me the mu, which maximizes this function. And that makes a ton of sense, because based on the intuition, the story we just said, the mu that maximizes this expected log likelihood is going to give me, on average, the highest likelihood for the values of x that are the most likely, which kind of makes all this information consistent with each other. And so that would be equal to mu1, and then you can kind of see what happens. Now the E and the M step just kind of trade off, one after another after another. So what would be the next thing that happens? The only change we would make is that this mu naught would now be mu1, my next best guess based on the last value of the M step. And then I would have a new expected log likelihood function here, which is a function of the next mu that I will propose, mu2. I would take the argmax over that function, and that would give me my next mu. I would replace this mu1 with a mu2. I would get my mu3, and so on and so on and so on, until some kind of convergence criteria is met, until these mu's are not moving so much. And then once it's converged, once I have my best value for mu, I think this is the best value for mu, then that will be the mu that I set. And then we know that once you have your value for mu, you've just fallen back into this first case, which is easy for us to get the best guess, the best estimate for the missing data point itself. So that is how you would solve this missing data problem using the EM algorithm. But more importantly, the intuition behind the EM algorithm is what I wanted you to take away from this video. Now let's close this video by talking about 2 questions that might be on your mind. I'll save the elephant in the room question for last. The first question that we'll talk about is what cases would you use this in? So one big case that this is used in is this missing data problems. So we have had a series of videos on this channel about missing data, how to deal with missing data, but we didn't talk about the EM algorithm in these videos. But you could definitely use the EM algorithm to simultaneously find the missing values, best estimates for some missing values in your data set, and also for the parameters that generated these values in the first place, which seems kind of magical. And that magicalness we'll get into our point number 2. But let me wrap up point number 1 here, which is that another big case this is used is in Gaussian mixture models, clustering models, basically where you're saying that I have a bunch of data points and they come from maybe one of 3 different classes. I don't know which data point belongs to which class. And I also don't know the distribution of the generating process within each class. So concretely, we would say that there's 3 classes. Each class has its own Gaussian distribution with its own mean, its own standard deviation. So it's the same flavor as this missing data problem. There's the mu and the sigma for these Gaussian distributions that generated the classes that I don't know. And I also don't know which data point should be in which class. And so I can use the EM algorithm in that case too to simultaneously find values for which data point belongs in which class, and also the means and standard deviations of the generating normal distributions of the classes themselves, and have good estimates for all of that at the end. So missing data problems, these kind of clustering generative data problems, are really big candidates for the EM algorithm. And now the elephant in the room, why does this work? Why is this guaranteed to converge to something that makes any sense at all? It bothered me for a long time, right? Like, it seems sensible. Everything we've said seems sensible. But it also doesn't seem like it would guarantee me to get where I'm trying to go, because when you take the derivative of a function and set it equal to 0, like you would in gradient descent, I mean, there's your guarantee. Like, you know that process works out. You've studied this enough times. This process, it doesn't seem like it would necessarily work 100% of the time. And so the proof is actually not too bad. I don't think I will do it on this channel unless there's interest. I could do the proof video, but you'll have to let me know. But the flavor, I can give you the flavor of the proof video. The flavor of the proof video is that we can show mathematically that after you do a E and an M step, you are in a better place in terms of your likelihood function than you were before. So in other words, whatever your likelihood function was before that E and M step, after you do the E and M step, your likelihood function has only gotten better. And if that's true every single time, and if the likelihood function has some kind of maximum, so maximum likelihood, then you're making your way towards that at least local optimum. And so that is the flavor of the proof. Again, probably won't do it on this channel unless there's enough interest, but it is a pretty cool proof to go through. So anyway, I think that's all I wanted to say on the EM algorithm. A very magical algorithm in stats and math indeed. I still kind of need to convince myself that it works sometimes, but it does work. If you have any questions at all, please leave them in the comments below. Thank you for watching, like and subscribe, and I will see you next time.